So in this video we will be discussing about first order reaction. First order reaction is a reaction in which in the rate law the rate of the reaction is only dependent on the concentration of a single species, that also raised to the power of 1. So in a single decomposition reaction we can write it as follows, that A gives product, and in the rate law we can write it as d epsilon by v dt is equal to Kc, that is the rate of the reaction is directly proportional to the concentration of the reactant. Now we need to make C as a function of epsilon by v to integrate it further. So we know that n is equal to n0 plus mu epsilon. This we have done in the first video, in which n is the concentration or the number of moles, in this case number of moles of reactants at a certain time. This is the number of moles of reactant, number of moles of reactant initially. This is the coefficient, positive for product, negative for reactant, and this is the, what is this, the epsilon, what we call, in which d epsilon by v dt is it gives the rate of the reaction. So epsilon gives us an idea about how much the reaction has gone forward. So as we are considering a reactant species in this case, so mu is equal to -1, and so the in the end the equation comes as follows: n is equal to n0 minus epsilon, and if we divide both sides with v, we get n by v equal to n0 by v minus epsilon by v. As n by v gives us concentration, so we can write C is equal to C0 minus epsilon by v. Now if we differentiate both sides with respect to t, we get dc dt equal to minus d epsilon by v dt. Now this term is rate, and it is equal to Kc, as we have seen before here, and again minus d epsilon by v dt is equal to dc dt here. So we can replace it and we can come to the conclusion of minus dc dt is equal to Kc. Now if we integrate the two sides where t is equal to 0, when t is equal to 0, that is at initial time, concentration is C0, so we integrate dc by c from C0 to c and Kt from 0 to t. This gives us minus ln C by C0 is equal to Kt, and our resultant equation comes as follows: C equal to C0 e to the power minus Kt. Thus, for a first order decomposition reaction, the concentration of A decreases exponentially with time. So if the graph is like this, but this is the concentration and this is the time, the concentration decreases exponentially with time. It decreases exponentially with time. Alright. Thus, if we measure and plot concentration of A with time, we will get a straight line with slope k for the reaction. So if we actually not plot concentration of A, this is wrong, we write it as ln C by C0 with time, that is the graph will be like this: ln C by C0, and here t, then the graph will be like this, straight line, right, and the slope will be equal to minus k. Okay, so now for calculation of half-life of a reaction, we know that at t equal to t half, we get C equal to half C0, means at half-life the concentration is just halved of the initial concentration. Now placing these values in the equation that we had previously, that is C equal to C0 e to the power minus kt, we will get half C0 equal to C0 e to the power minus k t to the power half. So that will give us in the end ln2 by k equal to t to the power half. So if we see that the half-life of a reaction is independent of the reactant's concentration, as we can see the t half's expression has no initial concentration in the equation, so it is independent of the reactant's initial concentration, then we can say that the reaction is a first order reaction. This is very important for examination purposes, as just by looking at the equation itself, if we see by plotting that the t half, the value of t half is independent of the initial concentration of the species, then we can find then we know that it is a first order reaction. Now considering an example of a first order reaction, we have discussed this before, that decomposition of N2O5 follows first order reaction. So the rate law will be given as follows: minus dCN2O5 dt, that is the differential of concentration of N2O5 with respect to time, will be equal to k into concentration of N2O5's concentration raised to the power 1, that is it will be dependent only on a single concentration term of N2O5. As observed that the rate law's order has nothing to do with the stoichiometric coefficient of a balanced chemical reaction, as in the balanced chemical reaction the coefficient is 2, but actually in the rate law the order with respect to the concentration of N2O5 is 1. Okay. Similarly, a radioactive decay is also a very good example of first order reaction. In this case, copper 64 unstable nuclei which disintegrates to form zinc 64 and beta particle. The half-life has been found to be 12.8 hours. So what do we do to find out the half-life of radioactive decay? First we come to the equation part. The rate equation can be written as follows, that minus dnn by n is equal to lambda dt, where lambda is equal to the rate constant, n is equal to the number of copper nuclei, and dn of this dn part is the number of copper nuclei that is being disintegrated in dt time. Now if we integrate the two terms, that is dn by n from initial concentration of copper nuclei to the number of copper nuclei that remains at time t, and the dt will integrate from 0 to t. So we'll get n is equal to n0 e to the power minus lambda t. This is very important for doing problems of radioactive disintegration. Now a very important formula for exams, it is usually given in problems, that suppose after 3 half-lives how much of a reactant will remain and how much will be disintegrated. So by using the following formula, n is equal to n0 into half to the power t by t half. So t by t half is actually the number of half-lives that has passed. The derivation is very easy and can be done by anyone. So suppose after 2 half-lives, it is said, please calculate how much of the reactant species will remain. So from this equation it is evident that n0 by 4 amount will still be remaining, still the number of copper nuclei that will be remaining in the reactant species. Similarly, after 4 half-lives, it will be n is equal to n0 half to the power 4, so the amount will be n0 by 16, that is the number of copper nuclei remaining after 4 half-lives has passed. Similarly, in the case of bacterial growth 2, first order reaction is followed. This brings us to the end of the video of first order reactions. In the next class, we will be discussing about second order reactions.